From our previous discussions, we know that all data processing activities happen inside the CPU. The CPU itself is a piece of digital electronic circuit that is made out of the basic building blocks of digital logic. The building blocks includes the AND gate, the OR gate, and the NOT gate. Now each of these building blocks is capable of implementing a Boolean logic function. But on the other hand, if you look at the type of operations that the CPU need to do, they involve much more complex tasks that include operations like adding numbers, subtracting numbers, multiplying numbers, dividing numbers, or operations like moving data from one place to another. How a piece of digital electronic circuit made using components that can only support basic logic functions implement these complex tasks. To understand this, let's look at a simple operation that a CPU can support and see how that can be implemented using a digital electronic circuit. For this purpose, let's discuss how an addition operation which can add two binary numbers be made using a digital circuit. For simplicity, we will consider only two 4-bit numbers, but the concept can be extended to add any large binary number. I have selected the two numbers and named them as number A and number B. Each of them will be a 4-bit binary number. I will do the addition one bit at a time from each number. So I'll start by adding the two least significant bits in both numbers. In this case, number A and number B has 0 and 1 respectively. When I add 0 plus 1, my result would be 1. There will not be any overflow to the next stage. Then I will add the next least significant bits in both numbers. In this case, number A and number B will have both 1 as the second least significant bit. When I add these two together, I get 0, but with a overflow to the next stage. In the third stage, when I add the two numbers which are 1 and a 0, I also need to consider the overflow from the previous stage. So altogether, I had a 1 plus 1 plus 0. Again, the result is 0 with a overflow to the next stage. In the fourth stage, I have two zeros at the input numbers. But with my overflow from the previous stage, now I have a result of 1 and without any overflow to any subsequent stage. So the result of my addition, which includes two 4-bit numbers, the first number is 0110, the second number is 0011, and the sum is 1001 with no overflow to the next stage. Now let's see how we can transform this addition process into a digital circuit made out of basic logic gates. The first step of doing this is to build a truth table. And even in my digital circuit, I am going to use a modular approach. I will first build a circuit which can add two 1-bit numbers from each of my inputs. And then I will replicate that circuit to add 4-bit numbers. So let's try to build the truth table for two 1-bit additions. The truth table will display all possible combinations of inputs and their corresponding outputs. My inputs here includes two 1-bit numbers, 1 bit from first number, that is number A, and 1 bit from the second number, that's number B, and also a third input which will tell me whether there was any overflow from the previous stage of the calculation, which I also need to consider here. Then I have two outputs. One is my sum result output and the other one will be a overflow which I will take to the next stage when I do this bit by bit addition. Once I have completed my truth table, from that data I can derive the logic expression for the two outputs. We will not go into the details of how these outputs are derived. But after simplification, we will see that the result output has 5 product terms combined with a OR gate. The overflow output, on the other hand, has three product terms combined with a OR gate. Then from this logic expression, I can go into building the schematic diagram of my circuit. The schematic diagram has altogether 8 AND gates and 2 OR gates and 3 NOT gates. The vertical lines represents the inputs from 2 bits and the overflow from the previous stage, and they are inverted values. Horizontal lines represents the first product terms, 8 product terms, 5 from the result output and 3 from the overflow output, and which are combined with OR gates to produce the final output. We will not go into details of designing this circuit either, because it is not within the scope of this module. So this circuit is capable of adding two 1-bit numbers considering the overflow from the previous stage and produce two 1-bit output, one specifying the sum output and the other one specifying the overflow to the next stage. The circuit itself is called 1-bit full adder. It is called a full adder because it can consider the overflow input from the previous stage. Our next task would be to use multiple instances of this circuit to build a 4-bit adder. So in the diagram given, you will see that there are 4 instances of the full adder circuit. In the lowest one, which deals with the least significant bit of the two numbers, I have preset the overflow input to a 0, which means that in the first stage there is no overflow coming from a previous stage. The overflow output of the first stage is fed back into the overflow output of the input of the second stage, and the overflow output from the second stage is cascaded again to the overflow input from the third stage. So likewise, we can keep on cascading these units to any number of bits to support the size of the binary words that you need to add. So by combining this, we get a adder circuit. Now in this case, we have a 4-bit adder circuit.